The maverick engineer Nikola Tesla made his contribution in the mechanical engineering field too. Look at one of his favorite inventions, a bladeless turbine or Tesla turbine. The Tesla turbine had a simple, unique design, yet it was able to beat the efficiency levels of steam turbines at the time. Normal turbines are complex in design, with blades of complicated geometry and stator parts. Nikola Tesla once said the Tesla turbine is his favorite invention, and he even claimed an efficiency level of 97% for this turbine. Let's start a design journey to understand this interesting piece of technology, and towards the end, we will also verify Tesla's efficiency claim. Modern-day turbines work on the airfoil principle. You can see the fluid gushing over the airfoil cross-section will generate lift force on it and make the blade turn. However, to make this turbine spin, Nikola Tesla relied on a totally different phenomenon, the viscous effect of fluid on solid surfaces. You might have seen this effect before. When water flows over a rounded stone, it makes the stone move because of the viscous force between the water and the stone surface. Nikola Tesla extrapolated this very force to run his turbine. Who knows, Tesla might have got inspiration for his turbine from this very example. If you produce the viscous force tangential to a disk, it will start to spin. Hooray! You've produced the simplest form of Tesla turbine. However, this is quite an inefficient turbine. Most of the jet's energy is lost here. Let's make this design more efficient and practical. Let's place this shaft disk pair inside a casing. Now the fluid enters through the outer casing, tangential to it. A provision for the fluid to exit is at the center of the turbine. Assume an inlet fluid with slightly higher pressure than the atmospheric pressure is entering the inlet nozzle at low speed. What do you think about the path this fluid takes? Since the fluid has a low velocity, the viscous force between the disk and the fluid will be very minimal, and the disk won't rotate. The exit hole is at atmospheric pressure, which means the fluid will have a slightly higher pressure than the atmosphere and naturally flows towards the center, almost in a straight line. Now, let's increase the fluid's speed and see what happens. Here, since the fluid has a greater speed, the interaction between the fluid and disk surface will produce sufficient viscous force to turn the disk. Here comes an interesting twist. When the fluid particles are rotating, they need a certain amount of centripetal force to maintain that motion. A fluid particle of the same velocity requires more centripetal force near the center than away from it. For this reason, the rotating fluid particles have a tendency to move away from the center. However, the turbine exit is at the center, so the fluid particles have to reach it eventually. Due to these opposing effects in the rotating case, the particle motion will curve out as shown. If you compare the radii of particle A in these two cases, clearly the curved path particles have more radius. Now, let's gradually increase the fluid speed. You can see the curvature of the fluid particles will further increase and form a kind of spiral. This concept is clearer when you track the same fluid particle for different disk speeds. The greater the disk speed, the more the particle moves away from the center. The fluid flow's spiral shape is in fact a blessing in disguise. The spiral shape increases the contact area between the fluid particles and the disk surface, thus increasing the viscous force production on the disk. This effect also means that the faster the turbine rotates, the more energy it will extract from the fluid. In other words, the Tesla turbine exhibits high efficiency during high-speed operations. To improve this design further, we need to understand a key concept called boundary layer thickness. We can observe in this system that the fluid particles which are in close contact with the disk adhere to it and form a stationary layer. The next layer of molecules tries to pull the stationary layer in the flow direction. However, in this process, they lose some energy to the stationary layer molecules. The same thing happens with subsequent layers. This tendency of fluid particles to resist the flow of the other particles is known as viscosity. In this way, you can clearly observe a velocity variation. The region up to which this velocity variation exists is known as boundary layer region. Clearly, inside the boundary layer, one fluid layer produces a drag force on the neighboring layer since a relative motion occurs between the layers. However, outside the boundary layer, no relative motion occurs between the layers, or the force between the layers is zero. To make use of this boundary layer phenomenon, Nikola Tesla came up with a unique idea. He added 2 more parallel disks. Now, let's observe the flow. A boundary layer is formed on every surface. As we saw earlier, the particles in the boundary layer region will try to drag or rotate the respective disk. However, you can see a region outside both the boundary layers where fluid particles are flowing freely, without any velocity gradient. This free flow does not impart any energy to the disk and contributes little to the torque generation. To make his turbine more efficient, Nikola Tesla brought the disks closer, keeping the gap approximately twice the boundary layer. Here, no free flow occurs. The 2 boundary layer regions are touching each other, and we can see the shear effects are now dominant in between the disk space. For steam, this ideal distance was found to be 0.4 millimeters. Using this method, Tesla improved the torque output of his turbine. Tesla found that by increasing the effective area between disk and fluid, the turbine can produce more torque. So he added more disks. This model had a diameter of 6 inches. However, this design failed horribly. The issue was that this turbine would run at a very high speed, 35,000 RPM. Nikola Tesla never thought that this turbine would produce such a high RPM, and the disk strength was not sufficient enough to withstand the huge centrifugal force produced in the material, resulting in material expansion and disk failure by warping. Nikola Tesla could not find any material to withstand such a high RPM at that time. Eventually, he had to reduce the RPM to less than 10,000 to save the disks from mechanical failure. Now for the big question. Despite the fact that Tesla turbines are so easy to construct, why aren't they used in the power generation industries? The reason is that the modern-day steam turbines are more than 90% efficient. We know that the Tesla turbine becomes more efficient as the rotor speed increases, but for the Tesla turbine to achieve such a high efficiency level, the rotor has to spin at a very high RPM, maybe 50,000. The major challenge is that for industrial applications, we need a disk size of 2 or 3 meters. Consider these hypothetical Tesla turbine disks with a diameter of 3 meters. It's an engineering impossibility to operate such large diameter disks at a speed of 50,000 RPM. The main issue is that of the blade tip velocity. The most modern steam turbine blades are able to achieve a Mach number of 1.8 at their tips, or 1.8 times the speed of sound. A rough calculation shows that these hypothetical disks will be having a Mach number of 13 at the tips. Definitely an engineering impossibility. The only option left is to reduce the RPM, and we know this act will lead to a huge drop in the turbine's efficiency. Therefore, Nikola Tesla's claim of 97% efficiency for his 6-inch model seems unrealistic. Remember, he was able to run this turbine only under less than 10,000 RPM. Despite these drawbacks, the Tesla turbine has found some niche applications. Interestingly, for instance, the Tesla turbine is reversible. It can work as a pump if you supply energy to the rotor. Also, we know that Tesla turbines work based on fluid's viscous effects. So these kinds of pumps are used in high viscosity applications like wastewater plants, the petroleum industry, and ventricular assistance pumps. Before you leave, don't forget to be a member of the Viscous team. Thank you.